Hello. Hello, good morning, good afternoon, wherever you might be. My name's Krish Narain. I'm one of the directors at Spantek Products, and welcome to our technical seminar on electrochemical gas sensors, covering a number of different topics such as their history, principles, different types, some indication on where future directions might lie. I would well, thank you all for attending. I can see on the chat that a number of people have saying hello already. I encourage you to do that. Let us know which country you're from as well. It's always interesting to see the breadth of the audience that we have and the scope that we have across the world. This lecture today will be given by Richard Chambers. Richard is now working at Solent Gas Consultants, but previously has worked for almost 15 years with City Technology, now Honeywell, working on as a technical role, working on support, collaboration, technical literature, a whole range of jobs, and is currently a member of the gas sensing group with the role of publications director. So has a lot of experience in that, and previously before that was at Solutron. So before I hand over to Richard, I will briefly just give a couple of notices. If you're interested in this type of seminar, please go to our Facebook page or our webpage and you'll see details of future seminars. The next one we have is in 2 weeks' time, on the 25th of my memory, which is looking at generating gases, in particular ozone, chlorine dioxide and chlorine, which are typically ones which are difficult to bottle at ppm level. With regards to this format of this seminar, we will have the main talk from Richard. After that, we will have a short 5 minutes from me on the background of Spantech, and then at the end we will take questions and answers. I hope to have 15 minutes available for that. If you have a question, please put it in the chat box. We will collect all of the questions, and we will try and answer every question at the end of the session. So just when you think of a question, just put it in the chat box. Sam, who's organising this and managing this, will pick up those questions and we'll answer them in the order that we receive them typically. Aside from that, I encourage you to ask questions because that does make for a much more interesting seminar. Aside from that, you'll see polling questions come up. There's 2 or 3 questions will come up during the course of the event, just getting some feedback on your background, and seeing who we got online, and there will be one handout that you can download on product portfolio. So I hope that all makes sense. And without further ado, I'll now hand over to Richard. As I say, Richard was a long time working for City, and before that with Solutron, and I think this will be, hopefully, it will be very interesting to look at electrochemical gas sensors. With that, so Richard, please take the stage.
Can you hear me? Good morning. Can you hear me? So I'm going to go through a presentation on electrochemical gas sensors. So firstly, a brief introduction to the history of the electrochemical gas sensor, how they function, what gases they can detect, a bit about some of the main applications, the different ranges of the gas sensors. I'll talk about the different sensing technologies and the pros and cons of those. Some typical issues that are faced in the field. Okay, so back in the 50s, there were electrochemical gas sensors around, but they were quite big. They were very power hungry. They were not suitable for for portable applications. So in the 70s, there were some researchers at the Wolfson Institute, and they came up with a miniature oxygen sensor built into a battery can or metal can oxygen sensor. These were very small. They became very suitable for portable gas detection. Then back in the 80s, this technology was developed, and this technology produced some toxic gas sensors. Since then, a number of different companies have produced these toxic gas sensors and oxygen gas sensors. They became very popular. They're very suitable for portable instrumentation. Since then, the technology has evolved. The basic technology has remained the same. The manufacturing techniques have improved. The quality has improved, and today they are looking to produce technical digital intelligence sensors, and that's where we're looking at moving forward in the industry today. So, how can I move forward? So, just a bit about how the sensors work. Basically, electrochemical gas sensors, they're fuel cells. The gas enters the sensor through a capillary hole, and that gas is either reduced or more commonly oxidized at an electrode. This produces a electric current proportional to the gas concentration. And so, in a bit more detail, basically what you've got here is a plastic container with a small capillary hole in the top. Now, this capillary hole, the dimensions and form of this capillary is very crucial. It's critical to the performance of the sensor. It's important that just about enough gas enters the sensor that can be reacted on the sensing electrode, but not too much that the electrode becomes overwhelmed or saturated. On top of this hole, you'll have a disc, typically made of PTFE, which is primarily to prevent dust and dirt from entering the sensor. Many sensors have a chemical filter in. Not all, just some, and this would be to remove any potential interfering gases. Inside the sensor, you've got a sensing electrode on the top there, which is where the gas would oxidize or reduce. You've got a counter electrode on the bottom, which would provide the balancing reaction to the sensing electrode, and in the sensor, you've got a reference electrode, which I won't go into details, but it basically enables the sensor to monitor higher concentrations of gas. And then you've got a electrolyte filling the sensor. That's often aqueous. Sometimes you could have gel or ionic liquids, but usually aqueous. So using carbon monoxide as an example, the carbon monoxide would diffuse into the sensor through the capillary hole, and when it comes into contact with the sensing electrode, it would oxidize, and you can see the reaction there. Carbon monoxide plus water gives you carbon dioxide, which will float off. Hydrogen ions, which would and enter the electrolyte, and some electrons which would flow through an external circuit. At the counter electrode, you would get a balancing reaction. So there you would get a reduction, and you can see the equation there, which produces water, which would go back into the electrolyte. So that water replaces the water that's used at the sensing electrode. And if you combine those two equations, you'll see that your carbon monoxide is oxidized into carbon dioxide. So you can see there that there's no consumables there. On most chemical sensors, you have no consumables. So in theory, the sensor should last for some years. There are a wide range of gases that can be detected by the chemical gas sensors. This isn't. There are probably more gases than this, but these are the common gases usually monitored. There are a wide range of applications. These are just a few of the key ones. The oil and gas industry, you're looking at commonly hydrocarbons and hydrogen sulfide. The semiconductor industry, often you'll have hydrogen used as a carrier gas. Chemical plants, a wide range of flammable gases and toxic gases. The power stations traditionally would be use coal and oil as a fuel. More recently, natural gas, which is mainly methane. The wastewater industry, the sewage gases, which give off methane and hydrogen sulfide. The wastewater treatment plants and boiler rooms, gas leaks, mainly flammable gas leaks and carbon monoxide from badly maintained boilers. Hospitals use oxygen and many different flammable and toxic gases. Tunnels and car parks, another common one. You're looking at vehicle emissions of carbon monoxide and various nitrogen oxides. So the different product ranges, there are various different formats of these sensors. They all function in much the same way. The difference are mainly in the different mechanical builds and sizes. The first was the metal can sensors mentioned earlier. They're still around, but less popular now because they're old technology. They're old. So the next range was the 3 series sensor. These are quite big. They're still used fairly commonly. People like them because they're robust and tough and well tested. But they are quite big. The 4 series was a smaller version. The technology in terms of the operation of chemistry is much the same, but it's in a much smaller format. And these are very popular still today and used in a lot of the portable instruments. The 5 series is a larger sensor designed for use in emissions. So it's got a larger volume of electrolytes, larger electrodes. It's better for use in emissions where you have more frequent high concentrations of gas. The 7 series is initially was designed for fixed instrumentation. It's still used widely. It's very popular. Again, very similar to the 4 series, but just a little bit larger. The micro was available in both LEL, micropel, and Toxics, microcells. They're very small. They're like almost like a postage stamp, about 3 millimeters deep. They're commonly used. BW use them a lot in the small portable products. And there's also a range of medical sensors, often with FDA approval. These two I'll skip over briefly, from where most of the audience here are used, replacement business. The 1 series and the Intelligence series are a reasonably new release. And this is the way I think industry is going to go. They're looking at the intelligent digital output sensors. Again, they're using electrochemical and Pellistor technology, but with digital output. So a quick comparison of the sensing technologies. The 2 common ones are catalytic and electrochemical. Obviously, catalytic are for combustibles, LEL gases. Electrochemicals are for oxygens and toxics. Both are fairly low cost. Electrochemical are popular part because they are low power. The downside is both types generally fail to danger. So steps need to be taken to bump test these on a regular basis, ideally before each shift, to just confirm that they're working correctly. Infrared, another popular technology. It's more expensive. You get 2 types. You have your point infrared, where you've got a sensor, and the gas has to be in contact with the sensor itself. You also have open path technology, where you'd have 2 units, and an infrared beam would be transmitted through an open space. That's very popular as well. And some semiconductor thermal conductivity and paper tape. These are still used, less so paper tape, but semiconductor and thermal conductivity definitely are still used. Right, cost sensitivity. So this is one of the main problems faced in the field. These sensors are designed to be as selective as possible to detect just the target gas, but in practice that's very difficult to do, and they will respond to other gases in the field. So this cost sensitivity can be positive or negative. So for positive cost sensitivities, if you have some interfering gases, then you would get an increase in the sensor signal, so potentially you would get false alarms, which can be costly. Negative cost sensitivities can be worse, because you could potentially come to a situation where there's a dangerous level of toxic gas present, but because the signal is reduced, then it may not alarm in dangerous situations, and obviously that would mean life may be at risk. There are certain things you can do to try and counteract this. I mean, commonly sensors would include filters, as I mentioned earlier, to chemically remove interfering gases. These filters tend not always to last the life of the sensor, and once a filter capacity is used up, then the sensor would start responding to interfering gases. Okay, so response to temperature, humidity, and pressure. Pressure generally is not a big problem, or not big response to steady state pressure. If you were to have a step change in pressure, then you will get a transient signal, as you see in the graph at the bottom. This will often result in a false alarm. This is often a problem when you're using pumps to pump the gas over the sensor. Pumps often use a chain of pulses, or pressure pulses, which will result in a chain of these transient spikes, which can then be read as a high signal. So care needs to be taken to design the gas delivery system when using pumps to make sure that the pressure pulses from the pump don't interfere with the sensor. So you have a steady state performance and transient performance. A steady state performance, pressure minimal, temperature and humidity more so. You can see on the graph at the top there, this is an example of temperature response. You see it's normalized at 100% at 20 degrees C. As the temperature increases, you can see that typically the sensor signal will also increase. The transient performance, again, spikes or step changes in pressure, humidity, or pressure will result in these transients. That will result in a likely false alarm. This often is an issue. Yeah, if you're leaving a warm building, going outside into a cold area, if you slam a car door, delivery pumps, this can be a problem in the field. Water transfer. So the electrolyte is often, or usually, aqueous based. There will be a certain level of humidity, ambient humidity, where the electrolyte will be at equilibrium. If the humidity is high, then the electrolyte will tend to absorb moisture, and this will happen faster at higher temperatures. As that absorbs moisture, its volume will increase. Generally, these sensors they will have a certain amount of free space within the sensor to allow for some absorption, but the point will come where the volume becomes too large and the sensor will fail. At low humidities, the opposite will happen. The electrolyte will lose water, and eventually the electrolyte will dry out to the extent where the sensor will fail. Now, usually you'll find that if you're using these in extreme humidities, you will get the moisture transfer, but if you put the sensor back into better conditions, it will tend to recover over time. Now, this is a model of how long a sensor may last in extreme conditions. So you can look up on here a temperature and a humidity, assuming it's constant. You can come up with an idea of roughly how long the sensor would last. You're looking at, in extremes, several months. This is a mathematical model which was put together, and it was found that it does tie in pretty closely with real life. Solvents. Again, this often happens in the field. Solvents do tend to attack plastics. If you look online, you can actually get some. There are places you can find out how various solvents attack various different plastics. Often ABS is used, and you tend to get micro cracking in the plastics, which can lead to mechanical failure of the sensor. We have found in the past that people would remove a sensor from an instrument, clean it with solvent, and then put it back in, and find that when they're screwing the thing back in, it would basically shatter. So solvents should be avoided wherever possible, whether it's in storage or within the application itself. Sensor saturation. So this commonly happens. The sensor is designed to measure up to a certain concentration. If the sensor is exposed to too high a concentration for a length of time, then it would become saturated, and you would then find that the output would become low, and its response and recovery would be very slow. Usually, when the sensor is put back into clean air, it will recover, but it could often take many hours to do so. So exposure to these sensors to very high concentrations over lengthy times should really be avoided. So the future of gas detection. The big thing lately, I'm sure you're all aware, is the Internet of Things, IoT, and a lot of work has been put into developing intelligent sensors and with digital outputs for use with the Internet of Things. And this means a lot of sensors would move from the conventional analog type to a digital type. So a lot of sensors nowadays, the new sensors will have a UART output, for example. Another big thing is miniaturization. There's a big push to have smaller sensors to be able to put them into smaller instrumentation. Okay, thank you.
Thank you for the talk. We had a few questions come in. We'll take those at the end of the session. So let's bring myself back on stage properly. And anyone else has to ask questions, we will we'll go through and answer the questions as best we can. I'll just now give you a short presentation, be 5 minutes or so, on Spantek Products, for those of you that don't know us, and what sort of what we're doing here in this space. As Richard, it's obvious what Richard is doing here talking, but what are we? So I think I've got about 7 slides. Spantek Products was formed in 1977, has been based in Surrey, in UK, it's the same place as now since 1984. Specialise in providing solutions for gas calibration problems. That covers a number of different things. So the most obvious ones is cylinders. We tend to supply 2 different types of cylinders. We tend to supply disposable cylinders. That's our speciality. Whether it be, in this case, you can see the porter gas cylinders. which are filled in the US, accredited to ISO standards, with some fairly unique cylinder treatments that allow reliable filling even down to 1 ppm H2S, and they're shipped around the world by us, where this accreditation in particular is needed, and where reliable gases needed, typically things like chlorine and H2S and things which are reactive. Those cylinders are manufactured in Houston in the US and Texas. We also have our own cylinders, which Spantek cylinders, which are filled often in the UK, but also filled in India and US with our partner companies. Spantech has a number of partner companies across the world, including in obviously India and US is safe there, but also Poland, and other parts of the group are in Wales and other parts of England. Typically, again, disposable cylinders up to 110 litres, batch certification provided, and we often put own labels on for companies who want to supply cylinders with their own name on. That's a very common thing for us to do. So you might get a cylinder in your lab with a different label, but behind it there might be a Spantek product. And we've been doing that for over 25 years now. Other products we do, we have a partner company in the US that manufactures handheld generators. I sort of put these into two brackets. These are pictures of the higher end generators, which you can select ppm levels, typically from 50 ppb or parts per billion up to about 50 ppm. Ammonia will go much higher. The gases that we're talking about are ozone, chlorine, chlorine dioxide, which are fairly difficult gases to bottle and at the ppm level reliably and store. So if you're particularly interested in those gases, we will have a seminar in 2 weeks directly related to those to the generation of those gases. And I think we'll put the link up to that in a minute. And hydrogen, ammonia, hydrogen sulfide, hydrogen cyanide, nitrogen dioxide, they're all gases, and the idea being that you can generate all these gases from a single unit. There is no actual gas stored; it's all generated on demand, which means that you can carry it on a plane, in the hold of a plane. So when I used to travel around and see customers around the world, I would just carry it with me in the hold in my luggage, which is much easier than shipping cylinders. The ongoing costs of these are very, very low. They are NIST traceable, calibrated to NIST calibration standards, and with certificates provided. And every 12 months you can recertify them, of course, to that. So I used to carry on a little Pelican case which would generate 8 different gases to NIST traceable standards, and I could jump on the plane with that quite happily. And in the lower end of the generators, there's the little ones which we make. These are often used for bump testing, but they can be used for continuous flow. They're not as accurate as the bigger ones, and they are fixed. They are fixed in their ppm levels, of course, typically between 1 and 25 ppm, and there's less options on the gases there. You can see the 4 standard ones there, but they do fit in your top pocket of your shirt, so they do have some advantages, and they could very well, often regarded as personal equipment, safety equipment in that respect. So very different there, but again, they're very much cheaper than the bigger ones. We're talking a few hundreds of pounds here. It depends what you do up to, rather than a couple of thousand for the bigger ones, or 3, give or take a bit. So these are but these are very simple to use, and they again have cells. So in the top, so the idea is the cell is consumed. It's a little bit like the opposite of an electrochemical cell, in that we use the gas in the flow stream to generate a current, which is measured. This is sorry, we use the current to generate the gas, which is then put into the flow stream. So getting that the opposite way around now. Yeah, very, very easy to use. There's just a single button on that one, for example, to press and hold for 3 seconds to generate the gas. Obviously, we deal with replacement gas sensors. We source from multiple manufacturers. Of course, we discuss your application. We've got 30 years of technical experience, and we will work with you to find the best solution. We operate 12-month drop shipment arrangements to reduce costs for customers, and various other ways we work with customers to get what they need at the best prices. We tend to oxygen sensors we tend to bulk buy in particular, and therefore pass on better pricing to customers, and be a little more flexible in the slab rates and the quantities rates. We've previously we do this with O2 sensors from City, for example, and 4OX, and this is 7OX equivalent at the moment, which is on the web page. So the essence is that's the company, but very quick run through Spantech. We don't do a lot of different products, but we do specialize in these calibration gas areas. A lot of very high technical support. The one product that's not up here is we also do rare gas purifiers as well, which is another big product for us. But you can see the link to our email, to our page, to our web page, and you can see we also have a link in Facebook, as you've seen. So that's very quick run through of Spantech. I hope it's interesting. You can download at the moment. It's on the handout tab, our product brochure, which covers all of these things in 4 pages, and gives you a quick overview of what I've talked about. Without further ado, then I will invite Richard back onto the stage, so we can run through the questions that were given to us during the course of his lecture. I will just run through and find them on the list. Okay, as Sam is queuing them up, but the first one, Richard, was how critical are the dimensions and other properties of the hole, the aperture opening that the gas diffuses into the cell? I think that refers to the picture of the cell that we had. We had up, I think, one of the slides.
Yeah, it's very critical. The obviously, the larger the hole.
Richard, I think you might be trying to talk, but you might be muted.
Okay. Can you hear me now?
Richard, I think you're muted at the moment.
Hello.
Richard, come back onto stage. Richard, we can see you now.
Hi there. Can you hear me?
Yeah, that's better.
Yeah.
The
capillary hole dimensions are very critical. Both the diameter of it and the form of it control the rate of diffusion of gas into the sensor. It's important that enough gas comes in to give you a decent signal, but not. It needs to be limited so that the sensing electrode can react all of the gas. If too much gas comes in, the sensing electrode will become overwhelmed or saturated, and you will not get an accurate reading. So another issue with the capillary hole is on certain sensors, for example, ozone and NO2 are two examples where you have quite large capillary holes. That also presents some challenges in terms of transient responses and humidity getting into the sensor. So yeah, it's very, very important.
Lovely, thank you, Richard. The next question I have is why do from Ganesh? Why do portable oxygen sensors get cracked or ruptured after some time of uses?
The usual reason for the sensors becoming cracked, mechanic damaged, is through solvent exposure, which would attack the plastic, and that would often cause micro cracks to occur in the plastic, which can result in mechanical failure.
Okay, lovely. And the next question is from Farah, who's from Honeywell. It says, are you going to touch on thermal conductivity gas sensors? So do you want to give a couple of sentences on those sort of things?
I'm not really very experienced in the thermal conductivity sensors. I'm more involved in the electrochemical and Pellistor type sensors.
Okay, lovely. Okay, so maybe something we can look at and do another seminar on. You never know. Just learn about those together.
Yeah.
Right. Brilliant. And then I have a next question from Bogesh, who says, so which would the best CO sensor be, which would you suggest for fixed and continuous monitoring in a robust mining application?
In a robust mining application, probably the best sensor I'm aware of would be the 4CM from City Technology. That was a top-end CO sensor designed specifically for the mining applications. I know that other manufacturers such as AlphaSense and DD Scientific also do CO sensors, but as far as I'm aware, the 4CM is probably the better sensor for that application.
Okay. Okay, and the next question will come up, I think, is from Michelle from Respo. What is the difference between point IR sensor and other IR sensors, which has IR source and mirror?
Okay.
Optics.
Yeah, so a point IR sensor would monitor the concentration of gas at a specific point. So the gas would need to come in contact with the sensor. A open path IR sensor, you would have a transmitter and a receiver at two different locations, and they would pass infrared beam through the air from the transmitter to the receiver, and it would monitor the gas levels over that path. So it would be able to measure gas concentration over a length, as opposed to just a single point.
Okay, right. Then I think we have the next one is from marketing. I think that's from Rockall. Can sensors be affected by strong external EM fields?
Yes, they can. Yeah, it doesn't happen a huge amount, but it does happen. These little sensors are basically aerials, and they are affected by these, and sometimes customers need to put these into a metallic housing, but especially with the metallic ring around the sensor, earthed, to minimise the effects of this. But yes, it can be affected by atmosphere field.
Okay, very good. The next question we have is from Ranjan Kumar. Is there a way to protect the electrochemical of the oxygen sensor when the electrolyte, maybe I think of the oxygen sensor when the detector is not in use?
I assume you're referring to the electrode drying out. Yeah, the best thing to do is just avoid keeping the sensor in extreme humidity levels, either high or low. Also, the rate at which the sensor will dry out or wet up is dependent on temperature, and it tends to only be a problem at higher temperatures. So if you keep the temperature low, that would minimise any issue.
Very good. Then from Bogesh, the question is, please suggest the Beck's oxygen sensor for fixed continuous monitoring for mining application.
Continuous.
Yes.
Yeah, so these sensors they're designed for industrial safety applications where continuous measurement isn't used. But for oxygen, they're obviously all fine for continuous use. It depends very much on the application. For industrial safety, the 4-oxysphere and the 7-oxysphere are good sensors. Alpha Sense and DD also do good oxygen sensors. There are other sensors, for medical applications and osmosis applications. So it does very much depend on the application.
Very good. I've got a quick note here from Spantech from the office to say that we will respond to the thermal conductivity sensor question directly. As we have more experience with that in the office. So just to go back on that one. The next question I have is from Alexandro from Italy, TechnoSense. I says, very interesting seminar. Do you think that a digital output standard would require higher validation and integration costs for the end user? Very, very interesting question, actually. Very good question.
Yeah. So these sensors tend to be a higher initial cost of the sensor themselves because there's a lot more technology in them. However, the implementation of them is much easier because these tend to have the same output regardless of the gas type or technology used. So potentially you could have a single circuit design and incorporate any sensor into that same design. So that is easier to do. Initial higher cost of the sensor itself, but lower cost of the actual design into the instrumentation.
Very good. Okay, another question from Bogesh. Again on the coal mining applications. What is the effect of the fine coal dust on the electrochemical sensors?
So you have generally a PTFE filter on the top of the sensor over the top of the capillary hole to filter out dust. What can happen, of course, is that if there's a lot of dirt, coal dust, whatever, that builds up on this hole, then potentially you could block the capillary hole, which would mean your gas wouldn't get into the sensor. And this, of course, would be a fails danger situation.
Okay. Brilliant. That's the end of the questions that we've had. I believe, just one last check before I say that. Just take the ones that have just come in. If MOX-1 sensors are used continuously, this is a question from Sanjay, then continuing in 95% oxygen plant, how long will the lifetime of the sensor be?
Okay, the MOX-1 is a lead-based sensor. It has a lead electrode, and as the oxygen reacts with that electrode, the lead will oxidize. And once that lead has been used up, it would no longer function. Now the data sheet states that I think for the MOX1, a typical life of about 2 years.
Okay. Very good. So typically 2 years, of course.
Yeah.
Okay. Then Michael from Singapore, old friend, so it's possible to get this. Yeah. Okay. So Michael, I'll come back to you directly on that because it's a porta gas question rather than a sensor question. Yeah, I'll just make a note. Let's see a scope. So 17034. Yep, Michael, we'll come back to you on that directly. Then from Supriya for Amatronics, what is the reason of the found counter, and what is the reason of the found counter and work and electrode short suddenly in working conditions in a toxic sensor?
They shouldn't short. If you've got a short, then you've probably got a faulty sensor.
Okay.
And that needs to be replaced.
Yes. So yeah, obviously if it's under warranty, then that's something that we would deal with typically for you. Bhagesh, as catalytic sensors, flammable gas detection, when they're working, they're oxygen dependent.
Yes.
Do we have any correlation graph between oxygen levels and performance?
I don't have a graph, no, but what you ideally want, you want between about 8% and 11% oxygen for a good operational sensor. If you get lower levels of oxygen, then what you would start happening, you rather than reacting the hydrocarbon into water and carbon dioxide, you would get some carbon monoxide produced, and hence the lower output. Ultimately, if your oxygen gets too low, you would start getting carbon produced, which would then soot up and block the reaction sites in the sensor. So
the follow up here was, if I put the catalytic sensor above 95% relative humidity in a condensing atmosphere, what reading will I get from methane?
So can you repeat that, sorry?
The question, the comment here, is a follow-up comment just came in, was if I put your catalytic sensor in above 95% RH condensing atmosphere,
yeah,
what reading will I get from methane?
Okay, the relative humidity would have a fairly minimal effect on the output for the methane. So I would, it shouldn't cause a problem.
Okay. And from last one we'll take, I think, is from Sanjay. Can we use the AO2 sensor for CO2 background gas?
Okay, so a lot of the oxygen sensors don't work well in the presence of CO2. City recommend that if you do have significant levels of CO2, you use the AO2, and that's because the AO2 is much better at dealing with carbon dioxide, but we would not recommend using it above about 25% CO2.
Okay. Lovely. Okay, I think we'll go at that point. We'll stop taking questions as we that's brought us nicely to our timed end of the lecture. Thank you very much, Richard, for your input. Appreciate it. It was a very interesting talk, and thank you for everyone who has put questions in, because that really does help at the end. Very interesting discussion. If you have any, you will at the end of this get a communication, literally right at the end of the seminar, so almost immediately, which will give you various contact details and ways to get further information. I also refer you to our webpage, as we've done before, the Facebook page and the LinkedIn page, much more so, and point of the next Spantek webinar, which is on the 21st of July at British time, 1 p.m. BST, which I think is 5:30 in India, to give you, which will be on generating difficult ppm level gases. Thank you for that. Those of you who have ticked the box to accept marketing, we will follow up with a version of the slide set. And as you know, the recordings, a link to the recording will be on the communication that follows this seminar. It'll also be on our webpage and our LinkedIn page as well. And you can see for India, our office has just put up their contact communications, contact details there. Spantek Products Calcutta, which is our partner company in India, based in Calcutta. If you want to talk to me directly, then my address will be on email address will be on the letter that follows, but I'll also put it up here at the same time, so you can get to me directly on that. Thank you very much for joining. Appreciate your time, appreciate the effort, and look forward to seeing you at our next seminar in 2 weeks' time, if at all possible. Thank you.
Thank you.
Thank you, everybody.